Hello, welcome back. In the second part of the magnetic field sensors video, we'll discuss the AMR, GMR and TMR based sensors. We'll start our discussion with AMR based sensors or the anisotropic magnetoresistor based sensors. So the AMR based sensors, they involve ferromagnetic metals or alloys. The material in the given shape is called as anisotropic magnetoresistor. The anisotropic magnetoresistivity is the difference between the resistivity ρ parallel and ρ perpendicular. What are ρ parallel and ρ perpendicular? Ρ parallel is resistivity that is measured when the current I is parallel to the magnetic moment vector M. Similarly, ρ perpendicular is the resistivity measured when current I is perpendicular to magnetic moment vector M. The anisotropic magnetoresistivity is ρ perpendicular minus ρ parallel. Since it is changing with respect to the relative angle between the direction of the current and magnetic moment vector M, one can write the resistvity's dependence on the relative angle phi between the current and the magnetic moment as rho of phi is equal to rho perpendicular plus rho parallel minus rho perpendicular into cos phi. The easy axis is defined like this. In a ferromagnetic thin film, the total magnetic moment vector M is aligned along an axis of lowest energy. This axis is called as the easy axis. In a ferromagnetic thin film, the total magnetic moment vector M is aligned along an axis of lowest energy. So in a ferromagnetic thin film, the total magnetic moment vector M is aligned along an axis of lowest energy, and that axis is called as easy axis. And in the presence of an external magnetic field, there is a dependence of magnetoresistance on the angle between the direction of the current and the magnetic moment vector M. For a simple specimen of a ferromagnetic material, the resulting resistance in the presence of an external magnetic field RH, which is equal to R0 minus delta R into H gamma by Hs whole square. RH is the resultant resistance in the presence of a magnetic field of strength H, and R0 is the resistance of the material when the magnetic field is 0, and delta R is the anisotropic magnetoresistance, H gamma is the rotation of the magnetic field, and Hs is the saturation magnetic field of the material. One can see that this expression has a quadratic behavior, but a quadratic behavior of these type of expressions will give rise to a zero sensitivity at low fields. The quadratic behavior of RH, because of the quadratic behavior of RH, sensitivity of the sensor vanishes for low external field. Since the sensitivity is not linear, it is having a quadratic behavior. For low external fields, the sensitivity vanishes. But a desired quality for a sensor is to have a linear behavior. To achieve linear sensitivity for the anisotropic magnetoresistor based sensors, one popular model exists to achieve that. The popular model is called as Barber's poles. Barber poles configuration that can rotate the current will give rise to linearity for the sensitivity of the sensor, and this configuration will have strips of good conducting metals are placed between strips of magnetoresistive material with lower conductivity. Generally, the material used is gold. So we'll have two strips of gold at the edges, and in between we have alternating layers of gold strips followed by ferromagnetic strips. This arrangement is called as Barber-Pols configuration. Using this configuration, one can linearize the sensitivity of the anisotropic magnetoresistors. Here HAPP is the H applied and HAN is the anisotropic magnetic field. Now we shall discuss the giant magnetoresistance based magnetic sensors. GMR is a thin film structure composed of a non-magnetic layer sandwiched between two magnetic layers. The resistance of the stack changes depending on the relative orientation of the magnetization of the two magnetic layers. In a thin film structure of a non-magnetic metal layer sandwiched between two magnetic layers, this structure is called as a GMR. Here we have two magnetic layers. The topmost layer is a magnetic layer and the bottommost layer also is a magnetic layer. Between these two layers we have a non-magnetic conductor that is sandwiched. This kind of a stack or this kind of a thin film arrangement is called as giant magnetoresistor. When the magnetization of the two layers is in the same direction, only electrons with one spin polarization are strongly scattered, due to which minimizing the resistance of the structure. On the other hand, when the magnetization of the layers is in the opposite direction, electrons with both up and down spin polarizations are strongly scattered, resulting in large resistance or high resistance. In a typical GMR, the layers will act as filters for the spin of the electrons. The layers act as filters for the spin. Depending on the spin of the electrons, the conductivity is going to change. As an extension to this observation, one can think of what is known as spin walls. In a typical GMR spin wall sensor, one of the two magnetic layers is fabricated to have fixed direction of magnetization, and this layer is called the pinned layer or the reference layer, meaning the magnetization direction is already fixed at the time of fabrication itself. The other layer is called as the free layer, meaning depending on the magnetic field direction, this layer is going to align in the field direction. The free layer is made up of a soft magnetic material, and the direction of magnetization of this layer rotates under the influence of the applied magnetic field. In case of a GMR device with minimum resistance R minimum and maximum resistance R maximum, the magnetoresistance ratio of the device can be written as the MR ratio can be written as R maximum minus R minimum upon R minimum. And when the magnetic field applied changes the orientation of the free layer, assuming that the pinned layer is oriented at an angle theta p and the free layer is oriented at theta f, the resistance of the GMR device can be expressed as R is equal to R minimum plus R minimum into MR into 1 minus cos theta f minus theta p 2. This kind of a resistance will result when we have the GMR in this fashion. The pinned layer is having magnetization along the x direction, and the free layer magnetization is now along the y direction. Potential difference will be along the z direction. So these two are orthogonal. Between these two layers we have the non-magnetic spacer. If the free layer is aligned orthogonally to the pinned layer as shown here, then one can write the resulting resistance as R minimum plus R minimum MR into 1 minus sin theta f upon 2. The resistance of the GMR device is proportional to the sine of the angle by which the free layer rotates under the influence of the applied field. For lower applied fields, sin theta f varies linearly with the magnetic field strength. Thus, the output of the sensor is linearized which is desirable for most sensor application. Now we shall see the tunnel magnetoresistance. Tunnel magnetoresistance sensor consists of two ferromagnetic layers separated by a tunneling barrier, hence also called as the magnetic tunnel junction. Tunnel magnetoresistance can be seen in magnetic tunnel junction, or for short called as MTJ. The sensor consists of two ferromagnetic layers separated by a tunneling barrier. The structure is similar to the GMR structure, with the conducting layer being replaced by an insulator. When two ferromagnets are magnetized in parallel direction, there is higher probability of the electrons to tunnel through the insulating layer than if the magnetization of the two layers are antiparallel. Thus, the parallel configuration results in minimum resistance and the antiparallel configuration results in maximum resistance. This is a typical magnetic tunnel junction. We have a magnetic layer, an insulating layer just below that. Below that we have another magnetic layer. When the two magnetic layers are aligned in the same direction, we'll have low resistance for the tunnel junction. Whereas in the case of anti-parallel alignment or opposite alignment of the magnetic layers, one can see higher resistance. In a typical TMR sensor, one of the ferromagnetic layers is free to rotate with the applied field, while the magnetization of the other layer is pinned. Just like the way we have seen in the case of a GMR, here also one layer is a free layer, the other one is a pinned layer. Resistance of the stack essentially depends on the cosine of the angles between the free layer and the pinned layer. In order to fabricate a TMR sensor with a linear response to an applied magnetic field, it is essential that the reference layer magnetization be pinned perpendicular to the free layer. The TMR sensors are more sensitive than GMR sensors. The TMR sensors have higher resistance and thereby consume lesser power than the GMR sensors. They suffer from high noise. They have high resistance and thereby consume less power than the GMR sensors at the same operating voltage. TMR sensors are more expensive and difficult to fabricate due to the need of high quality, pinhole free, extremely thin tunneling barrier. In this video, we have tried to explain what are AMR, GMR and TMR based magnetic field sensors. We have started our discussion with anisotropic magnetoresistors. These magnetoresistors are fabricated using ferromagnetic metals or alloys. Rho parallel is the resistivity measured when the current I is parallel to the magnetic moment vector M. If the current I is perpendicular to the magnetic moment vector M, then one can notice the resistivity, that is rho perpendicular. Anisotropic magnetoresistivity is the difference between rho parallel and rho perpendicular. The resistivity essentially depends on the angle between the current and the magnetic moment vector M. We have defined a new term called easy axis. In a ferromagnetic thin film, total magnetic moment vector M is aligned along an axis of lowest energy, and this axis is called as easy axis. The resultant resistance is having a quadratic behavior. As a result, for low fields, sensitivity of the sensor vanishes. To linearize the sensitivity, we have discussed one popular configuration, the Barber pole configuration. We have seen the giant magnetoresistance based sensors. The GMR is a thin film structure of a non-magnetic metal layer sandwiched between two magnetic layers. These layers, they act as filters for the spin. So one can think of spin walls. MR ratio is defined as R maximum minus R minimum by R minimum. We have discussed the tunnel magnetoresistance. We have said that TMR sensors are more sensitive over the GMR sensors. Further, the TMR sensors, they consume less power and they are prone to more noise. Thank you.